So we've been spending some time finding the areas of different figures. In 10.4, what we're going to do is take a look at specifically how the areas of similar figures relate to each other. Okay, objective, to find the perimeters and areas of similar figures. Now, here's what we're dealing with when we talk about the areas of similar figures. We have a rectangle, and let's say I want to double its side lengths. So let's make it about twice as wide and about twice as tall. Okay, doubling, at kind of first thought, we'd think that its area is going to double as well. But if we look here, the area didn't double. It actually looks like it got 1, 2, 3, 4 times as big. Okay, let's triple the side lengths. So let's say it's about 3 times as wide and 3 times as tall now. Okay, again, the area didn't just triple. It looks like in this case it got 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, 9 times bigger. Okay, the trick we see happening there is that when you double the side lengths, the area gets 2 squared times as big, so 4 times as big. Tripling the side lengths, we got 3 squared times as big, 9 times as big. Okay, and that works for a rectangle. And that's also going to hold true for any other polygon we look at. Okay, triangles, for example. If I take this triangle and I double its width, let's try that again. Double its width, double its height. Okay, it looks like 1, 2, 3. And if I flipped it upside down here, 4 of the original triangles, okay, it would fit in that triangle that's twice the size. So again, we see we have the 2 squared relationship. So in general, as far as how perimeters and areas of similar figures relate, we'll say if the scale factor of 2 similar figures is A over B, and remember with scale factor we're talking about ratio of side lengths. So if the side lengths relate to A over B, the ratio of their perimeters is just going to be that same A over B, okay, because perimeters deals with side lengths. But then the ratio of the areas is going to be A squared over B squared. Okay, so we see the squaring issue for the area here. Okay, so let's get into some problems and take a look at how that works. One, in A it says the rectangles below are similar. So similar, that's same shape, different size. The ratio of the lengths of the corresponding sides is 6 to 8, or 3/4. So I'd say that 3/4 is the ratio or the scale factor between these two shapes. Okay, what's the ratio, smaller to larger, of their perimeters? Well, perimeters are just based on the side lengths, so we'd say that's just 3/4. Second part, what's the ratio, again smaller to larger, of their areas? Okay, for the area ratio, what we'll do is we'll take that 3/4 and square the top and bottom, because our areas are coming from the side length squared. So we'd say the area ratio is 9 over 16. Okay, and that'll be the theorem we're using today. Perimeters are just the same as the scale factors of the side lengths. Areas will be the side lengths squared. Okay, part B is the same idea. Why don't you pause the video, try it, and then check your answer. Alright, so let's take a look at using that theorem to do some problem solving. Problem 2, part A says the area of the smaller regular hexagon is 127.3 feet squared. What's the best approximation for the area of the larger regular hexagon? Okay, so we have 2 regular hexagons, and kind of the thing that isn't said here, stated, is that they'll be similar to each other. Okay, since all their angles will be equal, their sides will be proportional. They'll all be 7 to 10. We know the area for the first one. It's 127.3 feet squared. And what we want to do here is we want to solve for the area of the larger one. Okay, similar figures to solve for side lengths. We always set up proportions. So let's do that. We can start with the scale factor, 7 over 10. Okay, is equal to, I know the area of the smaller figure, which is 127.3. And we want to solve for the area of the larger one. We'll call that x. Okay, set up the proportion. Now here's the big thing with this section. I can't solve that yet because as we saw just a second ago, the areas aren't proportional in the same way as the side lengths are or the scale factor is. So since we're dealing with areas here, I need to turn this into an area ratio. That's where we'll square the top and bottom. Okay, square both our side lengths. So the proportion we'll solve then will be 49 over 100 is equal to 127.3 over x. Okay, so once we turn this into an area proportion with area ratio equals area ratio, then we'll just cross multiply and divide. X times 49 will be 49x is equal to 100 times 127.3. Move the decimal place twice, 12730. And divide both sides by 49. We end up with our x is equal to 259.8, we could say. And then we solve for an area, so we'll say feet squared. Okay, so similar figures, we're using proportions once again, but then again pay attention to what we're solving for. Here it's an area, so we have to square those side lengths to make an area ratio. Okay, part B is the same idea. Pause the video, try it, then go and check your answer. In problem 3, we're just going to apply those same steps to a real-world situation. Okay, so applying area ratios. A says the scale factor of the dimensions of two pieces of window glass is 3 to 5. The smaller piece costs $2.50. How much should the larger piece cost? Okay, so here we're not solving for an area, we're solving for a cost. Okay, but anytime that cost is based on the area, such as with window glass or carpet or how much it costs to paint the wall, okay, we can set up the same type of proportion and solve. Okay, so we can take this scale factor again, 3 over 5, and set that equal to the smaller piece costs $2.50. Okay, the larger piece, we don't know how much it costs. Again here though, just like with our last problem, we're solving for something based on an area. Okay, the scale factor is based on the side lengths, so what we need to do is square those side lengths to come up with an area ratio. Okay, 3 squared is 9, 5 squared is 25, so we have 9 over 25 is equal to $2.50 over x. Okay, cross multiply and divide. X times 9 will give us a 9x is equal to 25 times 2.5 will be 62.5. Okay, then divide, we end up with x is equal to 6.94 repeating. So we'll just call that 6.94. And again, here we're talking dollars and cents. Okay, so same idea as our last problem, except for here we're solving for a cost based on an area. So we have to set up an area ratio by squaring the side lengths, solve the proportion, okay, by cross multiplying and dividing. Why don't you go ahead and give part B a shot. Okay, pause the video, try it out, then press play to check your answer. Alright, then in our last problem, we're going to work backwards. We're going to use the areas to solve for side lengths. Okay, A says the two rectangles are similar. The area of the smaller rectangle is 10 feet squared. what's the value of x? So what's this side length here? Okay, we know our first area is 10 feet squared. Okay, this problem doesn't give me the second area, but I can figure that out easy enough. Base times height, 20 times 8 will give me 160 feet squared. Okay, and what I can do then is I can set up a ratio. We can say that 10 over 160 is equal to x, which we don't know, over its corresponding side, 8. Now, again, we have a problem, though, because the 10 over 160, that's an area. X over 8, those are side lengths. And we know the two aren't proportional to each other. Okay, and our last set of problems to get from side lengths to areas we squared. Here what we're going to do is we're going to take the square root of my side lengths, the areas, to get from the areas back to the side lengths. Okay, to do that, square root 10, square root 160 aren't going to work out very nicely, so I'm going to reduce this fraction first. 10 divided by 160 is just going to reduce down to 1/16. Okay, so again, that's a set of areas. We need to square root that to get my side length ratio. Okay, square root of 1 is just a 1, and square root 16 is 4. So we could say 1/4 is equal to x over 8. Okay, cross multiply and divide, we end up with x is equal to 2. And in this case, I'd say 2 feet not squared, because again, what we solved here for here was a side length and not an area. Okay, so again, what we did in problem 4 is just work backwards from problems 1, 2, and 3. If we know the areas and we want to solve for a side length, we have to take the square root of those areas to come up with a side length scale factor. Okay, one more time, pause the video, give part B a shot, okay, and then hit play to check your answer.